Assalamualaikum warahmatullahi wabarakatuh and good evening. My name is we are from group 8. My name is Hazrul Mustaqim bin Muhammad Qasim. My group member is Hairul Faizi bin Hairul Nizam and Wan Ahmad Aiman bin Wan Dawud. So our group topic is Runge Kutta. So in this presentation, I will start with the history of Runge Kutta, and then the theory, the question, and the application of Runge Kutta. So the history of Runge Kutta method is the Runge Kutta method actually was developed by two German men, which is named Karl Runge and Martin Kutta in 1901. So basically the name of Runge Kutta came from the name of the two German men who is developed the method. Karl Runge developed numerical methods for solving the differential equations that arose in his study of atomic spectra. These numerical methods are still used today. While Kutta, another German applied mathematician, he is also remembered for his contribution to the differential equations base, which is Kutta-Joukowski theory of airfoil lift in aerodynamics. Definition of concepts. So basically the fourth order Runge-Kutta method, also known as RK4 or the Runge-Kutta method, is one of the most popular methods of solving ODE. In numerical analysis, the Runge-Kutta methods are a family of implicit and explicit iterative methods, an effective and widely used method for solving the initial value problems of differential equations. It can be used, Runge-Kutta can be used to construct high order accurate numerical method by function self without needing the high order derivative of functions. And then the idea. So the basic idea of all Runge-Kutta methods is to move from step yi to yi plus 1 by multiplying some estimated slope by a time step. Then the difference between particular implementations involve how one estimates the slope in the fourth order Runge-Kutta method we will study. The basic idea is to combine 4 preliminary estimates to get one really good slope. So as you can see in the diagram below, we start at a location yi at a time ti, and we want to figure out the value of y at the time ti plus 1. So we make 4 estimates of the slope within this time interval. Next, K1 is the slope evaluated at the starting location yi, which is black dash line in figure. We project this slope forward by half a time step to determine an estimated position, which is the green dot, at this future time. Next, K2 is the slope evaluated at the location y1, which is the green dash line in figure. You can see here. And then we project this slope forward from the starting point by half a time step to determine an estimated position, which is the brown dot, at this future time. While K3 is the slope evaluated at the location y2, which is the brown dash line in figure, the longest one. And then we project this slope forward from the starting point by a full time step to determine an estimated position, which is the pink dot we can see here, at the next time step. K4 is the slope evaluated at the location y3, which is the pink dash line in figure here. Once we have these 4 slopes, we can combine them in weighted fashion to create an average slope and use the average slope to compute the next position. So here is the example for the use of Runge Kutta method of order 4 to solve the following using a step size of h equal to 0.1 for 0 is lower or equal x, lower or equal 1. So you can see here y in bracket 0.1 equal to 0.9655827899, and this is the graph, this is the table for x, y, k1, k2, k3 and k4, and this is the graph that was made by us. So you can see the shape of the line. So for example 2, solve the following using RK4 Runge Kutta method of order 4 for 0 below or equal x, below or equal to. Use a step size of h equal to 0.2. Then we will substitute k1 equal to hf in bracket xy, then we will substitute h with 0.2 as stated in the question. And y 0.2 equal to 5.512400893. And again, this is the table for the x, y, k1, k2, k3 and k4. This is the graph. You can see that it's rise from 5 to 6 and 6 something, and then it's stepping down again to below than 2 when x equal to 2. So for the example 3, we have to solve the following using RK4, which is Runge Kutta method of order 4 for 0 below equal x or below 0.6, and we have to use a step size of h equal to 0.1. So you can see here the solution, and y is 0.1 equal to 1.1164918, and this is the table for the example 3. And this is the graph that were made for the example 3. So for the x 0, y 1, and then it rise until 0.6. So lastly will be the application of Runge Kutta. So a ball at 1200 Kelvin is allowed to cool down in air at an ambient temperature of 300 Kelvin. Assuming heat is lost only due to radiation, the differential equation for the temperature of the ball is given by, so you can see the equation here, d theta dt equal to negative 2.2067 multiplied by 10 power of negative 12, and then in a bracket theta power of 4 minus 81 multiplied by 10 power of 8, close bracket, and then the theta 0 equal to 1200 Kelvin, where theta is in K and T is in seconds. Find the temperature at T equal to 480 seconds using Runge Kutta first order method. Assume a step size of h equal to 240 seconds. So we were asked to use a step size of h, which is 240 seconds. So here is the solution. Here, this is the first step, and then this, as we were asked to use h equal to 240 seconds, then we have to substitute the h with 240 seconds, but we have to find the k1, k2, k3, k4, and then this is next. And this is the graph you can see here as figure 1, which is figure 1. It compared the exact solution with the numerical solution using the Runge Kutta Fourth order method with different step size. So this is the step size for 120, this is the step size for 240, and this is the step size for 480. Comparison of Runge Kutta Fourth order method with exact solution for different step size. So table 1 and figure 2 show the effect of step size on the value of the calculated temperature at t equal to 480 seconds. So as we can see in table 1, value of temperature at time, which is t equal to 480 seconds for different step size. So this is for the theta, the temperature, So in figure 3, we are comparing the exact result with Euler's method, which is Runge Kutta first order method, Hume's method, which is Runge Kutta second order method, and Runge Kutta fourth order method. The formula described in this chapter was developed by Runge. This formula is same as Simpson's 1/3 rule. If f x, y were only a function of x, they are only versions of fourth order method, just like there are several versions of the second order method. The formula developed by Kutta is here, you can see here the formula, and where k1, k2, k3, and k4. So this formula is the same as the Simpson's 3/8 rule. If f bracket x comma y is only a function of x. So we can see figure 3 is the comparison of Runge Kutta method of first, Euler, second, and fourth order. So I think that's all from us. Thank you.